And I think we can start. And so today we have two speakers. And the first one is going to be Mauro Porta. And the title of his talk is Pro and Ind Categories in Algebra and Geometry. And Mauro, you can start whenever you feel ready.
Yeah. Okay, thank you very much for the invitation. It's a pleasure to be speaking here. So, so today I want to tell you some sort of a story about the natural appearances of pro and Ind objects and then pro and Ind categories in situations from algebra and geometry. So it will mostly some sort of long series of examples, and then there will be some speculation at the very end. And some questions for those who want to discuss. So so the starting point is the following. We have I assume that everybody here knows the pro and Ind construction, and this thing is very useful in algebraic geometry, and it appears in algebraic geometry. Let me give just a couple of examples. Well, the first and perhaps more important thing is when X is a quasi-compact, quasi-separated. So, sorry, just a disclaimer. The disclaimer is that everything happens in the infinity categorical setting, unless I say otherwise. It's not really important for the talk of today, but I just refer to them in my intuition works for that. So if there is something that cannot work in the classical setting, then that's the reason. So so let's say that X is a quasi-compact, quasi-separated derived scheme, not really necessarily derived, but anyway, then quasi-co on X, it's Ind of perf of X. Okay. So, so this is like a pretty convenient way of reducing questions about an unwieldy category like a quasi-co X to questions about its compact generators, which somehow is easier to grasp. I mean, many results, we will see a couple are true for perf. And so, okay, another instance of using pro and Ind construction is if we want to look at formal schemes, then these are like naturally inside Ind of derived stacks, because I mean the key point is that SPF of some ring, local ring A, let's say, or complete ring with respect to some it froze.
Excuse me, Mauro. I think okay.
Yeah.
We lost your screen.
Yeah. Is that this thing is a colimit in of spec A modulo AIN. The colimit is a priori, it's done inside pre-sheaves of affines. And now the point is that since the transition map are closed immersion, closed immersion, this actually is an Ind object. Okay, And there are other examples. So in geometric Langlands, we often want to study objects like the affine Grassmannian. The affine Grassmannian, and this is an Ind stack. Okay, and so, and of course I forgot one that I should have said before, which is algebras. So derived affine, let's say. This is Ind of algebras of finite type. Okay, and so I mean these are like pretty much standard occurrences of the Ind construction. And let me take this example and let's look a little bit more about what's going on there. So example, we take an algebra, not necessarily of finite type, not of finite type. Then we can approximate it as a colimit of A alpha, where this is a filtered colimit of algebras of finite type. Okay, and well, I will use a Kashiwara-Shapira notation to denote that I can actually consider this thing as an Ind object. And so if I have this diagram, the Ind object defining A via this equivalence, then I can associate some fine invariant, let's say, which is some sort of different version of the category of A modules. I could look at A mod, let me call them Ind, which is a colimit alpha of A alpha mod. And this I want to see it as an object in Ind cat infinity. If you prefer, you can put PRL, doesn't, it's not really important for the talk of today. Okay. Okay, so we can consider this thing. And well, the natural question is, what's the relation between A mod, the category that we are all used to consider, and A mod Ind. Of course, there is a natural functor, I mean a morphism in the cat that goes from A mod Ind to A mod, which is, informally speaking, it's taking some sequence, I mean some object F alpha, say, and it's sending it to F alpha tensor A alpha with A. Okay, and now the point is that well, phi restricts to perf, let's call it phi perf, that goes from colimit of perf A alpha to perf of A in Ind cat infinity. And now claim is that phi perf is an equivalence after realization. What I call realization is the functor that goes from Ind-cat to cat infinity. Just take the colimit. So in other words, I'm saying that we have an equivalence colimit of perf A alpha equivalent to perf of A. Okay, so this is what is called the Noetherian approximation, the content of Noetherian approximation. It's extremely useful in classical algebraic geometry because essentially it allows to reduce questions on non-Noetherian schemes, non-Noetherian algebras to questions on Noetherian ones by approximating them by things of finite type and using the fact that the derived category somehow behaves well under this approximation. But so this object, what I want to point out is that this phi perf is not an equivalence before taking the realization. And the reason is very simple. So take, however, phi perf is not an equivalence before taking realization. And the reason is that if it were, then for any infinity category C, we would have that functors from C to colimit of perf A alpha. Well, these are I computed inside the Ind-cat. So this is a colimit of functors from C to perf A alpha. But on the other hand, this would also be functors from C to perf. Now, if C was a finite category, there would be no problem. Essentially because of this equivalence. So any object mapped there, it can be lifted. The perfect complexes are defined by finitely many equations, so let's say, because it's the smallest full subcategory of A mod containing the structure sheaf and closed on the finite limits and colimits and retracts. And morphism also, because we apply the same argument to the home F dual tensor G, which is still a perfect complex. But what happens when C is infinitary? I mean, we have infinitely many morphisms. Then we cannot just lift all the relations that are needed to get a functor to this diagram. So this equivalence here is definitely false. Cannot be true. Okay, so phi perf cannot be an equivalence, which means that this object contains strictly more information than these other objects. When A is of finite type, there is no difference between the two. But when A is of not of finite type, then we have some strictly finer invariant, out of which we can recover the other one by taking realization, thanks to this observation here. And the question is, how much do we care about this finer invariant? So the key question of today is how much do we care about A mod in let's say, let me say, in the daily practice of an algebraic geometry. Okay, and the answer is that, well, we don't care that much, but there are definitely some situations where it's useful to remember that we might have lost information. So in average, not much, but sometimes it saves the day to remember we lost some information. And so the
Mauro, I
yeah.
think it froze.
It froze again?
No, now it's fine. Now it's fine. I apologize. Now it's fine. Sorry.
Yeah, thanks. Yeah, do not hesitate because it will really do. Okay, so so the goal of this talk is to provide some example. Okay, and I have two main sources of examples. So the first one will be analytic geometry, and the second one will be geometric representation theory. So the first one is example from analytic geometry. And maybe let me say that I mostly care about complex analytic geometry because in non-Archimedean analytic geometry, the situation is somehow simpler. We do not need all this machine. And so let me start with some basic setup to make you understand the example. So the setup is the following. We take X, a complex analytic space. So this is, for those who don't know, it's just like defined as a schema. It's essentially you start with some disk inside some Cn. You take some ideal of holomorphic functions of X. These are holomorphic functions. And then you look at the zero locus of this thing, zero locus. And this will cut something which could be like arbitrarily bad, with very bad singularities, and these are the local models, and then we glue them in the usual way. Okay, so we take a complex analytic space and we give the following definition, which is X is said to be Stein if for every coherent sheaf, I write the heart to mean that it's discrete, it's the usual abelian category of coherent sheaves. One has H1 of X with coefficients in G is 0. And so little remark is that if X were a schema, this condition would imply that X is affine. This is a Serre cohomological criterion for affineness. And so we could write X isomorphic to spec A, and so we would get that quasi-co on X is equivalent to A mod. Okay, and this is somehow the basis for the coherent theory of in algebraic geometry, because then you know what your category of sheaves, the category of sheaves that you want to consider on affines, and you glue them by descent, and you get the same category defined for all kinds of objects in algebraic geometry. So that's very better. Not only this, but it also reduces geometric questions about some category of sheaves to completely algebraic questions about modules over some ring, which is arguably easier. I mean, we have a whole different set of machine attack questions there. So okay, so the natural question is, can we have something similar in the analytic setting? So question is, can we have something similar in the complex analytic setting? And unfortunately, the answer is no. Okay, so yeah, that's very unfortunate, and in the sense that there are examples of Stein spaces where the category of coherent sheaves on X is not equivalent to the category of modules of finite type over the global sections of X, holomorphic functions of X. There exist examples of X Stein such that coherent sheaves on X is not equivalent to modules AX modules of finite type, where AX is gamma X of X. So entire holomorphic functions. And what is the main problem? The main problem is that being coherent is a local condition. There exists some coherent sheaf here, such that the global sections is not of finite type as AX module. And if you think it's not so weird. The point is that if this is our space X, because we are working in the analytic setting, not only the analytic setting, but because we are working in the analytic topology, then we can have a very bad cover. I mean, in particular, infinite covers. And so the point is the condition where of G being coherent means that locally it's a quotient of OX power n, but this cover could be infinite, and in the end you will need like an increasing number of generators to describe G over the whole X. This doesn't happen in algebraic geometry because affine schemes are quasi-compact. So every cover you can automatically define it with finite cover. Then somehow you pick all the generators and it's still a finite number, and it's okay. So how can we fix this thing? Okay, and the key idea is the following. So we say that so consider the following objects. So definition, X complex analytic, a compact Stein in X is a compact.
Mauro?
Yeah, it's Rose. A compact subset K of X, admitting a fundamental system of Stein open neighborhoods U alpha. Okay, so let me give you an example. You take X to be just C, okay, and you take as a compact subset the closed unit disk. Okay, this is X, and we take K equal D. So these are complex numbers whose norm is less or equal to 1. Now, the point is that this cannot be an analytic space, complex analytic space, because there is some border, which is the real analytic stuff. So this goes out to the complex analytic category. But it's not really a problem, because what you can do is you can find some fundamental system of open neighborhoods, something like this, that approximate your thing. Okay, and so the idea is that we can make this object enter again in our category by considering it as a pro-object. So as a functor point, it makes sense to consider K as an Ind complex analytic space. Okay, and now this is interesting because we can prove one can prove the following theorem. So we take a K inside X and compact sign. Then there exists an equivalence between colimit of perf on U alpha and colimit on perf of A U alpha, where alpha ranges over Stein neighborhoods of K, and moreover, this equivalence can be lifted to an equivalence between Ind objects. Okay, in the cut infinity. Okay, and this is actually pretty great because this is saying that I mean, this is the analog of what was happening here. Somehow it's even stronger in the sense that these algebras here are not of finite type. These objects are of finite type in the analytic setting, but not in the algebraic world. And we have a very strong equivalence because, I mean, of course, if you know this thing, then this follows by taking realization. But this is some sort of universal thing because corollary of this is that for every infinity category C, we have functors from we have colimit alpha of functors from C to perf U alpha is equivalent to colimit alpha functors from C to perf A U alpha. And of course, if you only knew this thing, there would be no way to deduce this thing. Yeah, so I was led to consider this this kind. So this theorem is Holstein and myself. And the point is that this equivalence, not at the level of the derived category, let's say, but for the usual category of coherent sheaves, abelian category, it was kind of known, not written like this, but this statement here is completely, I mean, it was really us, and it improves a lot. And the reason why we wanted to consider this thing was exactly because at some point we realized our goal was to develop some sort of Tanaka duality in the analytic setting to study Riemann-Hilbert problem. And in developing this Tanaka duality, we were like trying to reduce question to algebraic setting, and we kind of needed this equivalence where C was not compact. So in the end, we managed to prove this equivalence, which has overkills, definitely overkills the problem. So this is one first example in the analytic setting of like why could it be natural and why it could save the day to remember that we should not just work with the realization of an Ind object, but actually with the Ind object itself, even if it's an object that not many people considered before. Yeah, so this is the first example. Is there some questions on this? No? Okay. So let me give a second example. So this comes from geometric representation theory. And more precisely, all algebras.
Sorry, Mauro, can I ask you a question maybe?
Yeah.
At the very beginning, at some point you said, this is not true at this level, but it is true if you compute the geometric realization. And you gave us a reason for which it was not true before computing the geometric realization.
Yeah, so...
Can you tell us why it is true when we compute the geometric, why the same problem doesn't happen?
When we computed the geometric realization, you mean?
Yes, because you gave us a reason for which it doesn't work before, but you didn't tell us why it works after.
Well, I said that it's a Noetherian approximation. I was kind of assuming it was known, but the point is that it's not difficult. So for fully faithfulness of this functor, so this is the functor after geometric realization. So because this is a filtered colimit, morphisms are computed as a colimit of map in a gamma, let's say gamma bigger than alpha, of f alpha tensor a alpha a gamma, and g alpha tensor a alpha a gamma. Okay. But because f and g are perfect, we can rewrite this thing as a big tensor product. And then this colimit commutes with the tensor product in all the variables. And so, but the colimit of the A alpha is A. So in the end, this becomes the same thing as map in A from F alpha tensor A alpha A, G alpha tensor A alpha A. And so this is fully faithfulness. And now for essential surjectivity, what happens is that what is a perfect complex is something that comes from, I mean, it's the smallest full subcategory of perf of A mod that contains A and is closed under finite colimits and retracts. Now take a finite colimit diagram. Because of fully faithfulness, you can lift it to a finite point in the colimit. And then you just take the colimit there, and that gives you a lift. Same thing for retracts. So the point is that, yeah, so this is why it's essentially subjective, and in the end, why this is an equivalent. And so what is the difference? Maybe the real question is, the real interrogative is, what is the difference between this thing and this thing? And what I would like to say is that somehow the intuition is that this category should rather be looked at as some sort of enriched category, enriched in some category of in spaces, actually pro-in spaces, because morphism in this filtered colimit actually have a canonical Ind-pro structure. And so it would be like more natural to look at this category as something enriched in pro-Ind, and forget the Ind structure of the category itself. I mean, do not look at it as an object in Ind-cat, but look at it as a category enriched in some sort of topological vector space, topological spaces somehow. But I will come back to this point a little bit later. So yeah, I mean, what I wanted to say is that it can be actually useful. This it throws. It can actually be useful to look at this kind of objects, because if you can prove something like this, then you well, it's essentially like you're looking at morphism of spaces, and you know that it's homotopy equivalence, like you have an explicit homotopy against it's a weak homotopy equivalence. I mean, if you know these, it's almost like having the explicit homotopy, so it's preserved by any operation that you can do to this thing. Okay, so let me give another example. Yeah, so here the setup is quite different. Let me just simplify at most the thing. So we take X to be a curve or a surface. Let's say over C. And to this thing, we can associate a moduli space, co X, which is the moduli of flat families of coherent sheaves on X. Okay, and in representation theory, it's very interesting to look at the homology of co-X. And one slogan, one example, it's a result of Maulik Okunkov. It explains why we might care about this kind of objects. It's because when X is a K3 surface, then co-X is hyperkähler. Okay, and there exists some conjectures of Claire-Voisin on algebraic cycles on this thing. And the idea is that if we use, if we study its homology, and we look in particular at what we call the whole algebra structure, the whole product on co-X produces enough information to tackle this conjecture. I won't go into the details, but imagine that this conjecture is saying something about a cycle map being injective. The cycle map is comparing the cohomology of this stack against the Borel-Moore homology of its analytification. And the conjecture says that this map is injective, at least on a large class of sub-ring. And okay, so the idea is that this whole product produces some very big infinite dimensional Lie algebra that acts in a geometric way on this thing. And therefore, it acts on both algebraic cycles and cohomology classes in equivariant way. And now, if you study, if you can arrive to identify what is this big Lie algebra, you realize that you actually know all its representations, and you can prove that the ring, the cohomology ring was N was interested in, was irreducible representation of this Lie algebra. So any map of representation that goes out to something irreducible is forced to be injective, which is the content of the conjecture. So anyway, that's not the point of this talk to explain this idea, but I want to say that there are very strong geometric reasons behind looking at the homology of this kind of objects. And okay, the main homology theory that we care about is G theory. So Grothendieck group of coherent sheaves. So in the end, we're gonna end up looking at something like this, G of co, and we want to construct a whole product. The idea is very simple. We construct it as an explicit push-pull correspondence. We look at the stack of extensions, short exact sequences of coherent sheaves, and this is G0 of cox, and let's say if we have a short exact sequence f prime f second, this thing is sent to the middle term here, and it's sent to f prime f second there, and then you do push pull. And this thing gives you a map like this at the level of homology, which is a associative multiplication on this set, which is called the whole product. Now, the problem is that co is not quasi-compact.
Mauro, maybe just an information for you.
Yes.
You have 7 to 8 minutes.
Do I have what?
7 to 8 minutes.
Yeah. Okay. So the problem is that this thing is not quasi-compact, and so classically, we fix this thing by introducing, look at some topology on G0 of cox. What is this topology? Open neighborhoods of 0 are given by classes supported away from some quasi-compact open. Okay, so it turns out that a very interesting question to pose is to try to categorify this statement. So this is the G theory. It's the K theory, the Grothendieck group of the derived category coherent sheaves on this stack. And for certain kind of problem, like related to categorical Donaldson-Thomas invariants, we definitely want to categorize this thing. So we want to have some sort of derived category where there is a symmetric E1 monoidal tensor structure, which induces the whole product after passing to K0. So it's important to categorize this construction. So essentially, instead of looking at G0 of co-X, we want now to look at the derived category co-bounded of co-X. And we want to put some associative, E1 monoidal tensor structure. And now the question is, how do we categorize the topology? I mean, I don't have time to actually explain why this topology is important, but let's say that in order to actually make some computation with this convolution product, it's important to think in terms of this topology, because classes will be identified and we will have infinite sums in order to actually be able to make sense of all the computations we want to make, and this topology plays a big role in making this possible. So it's very natural to see, since this is a very important tool, how do we categorize that? And the answer is pretty simple in this case. It's replace co by the Ind object given by open exhaustion by quasi-compact open substack. Okay, so for those who know a little bit, the thing is that this symmetric monoidal structure comes from what is called a two-Seagal structure, and this topology that people are considered is not really defined as I'm defining it now, but it was more like defined in terms of a very explicit exhaustion made by very explicit open substack that are quasi-compact in terms of Harder-Narasimhan filtration. And the problem is that when you try to make this very explicit filtration and the two-Seagal condition interplay, then you're going to have lots of problems, because the exhaustion on this guy induced from this map is different from the one induced from this map. And so you end up having to refine the open exhaustion of this guy in order to make it compatible with both. And people in representation theory were becoming kind of mad because they wanted a very explicit exhaustion. But it's not important. The point is that if we work with the Ind object structure and we consider all the open exhaustions at the same time, then this ambiguity does not create, and we can just solve it and get a canonical two-Seagal object in Ind stacks. So that's pretty useful. But then, of course, we want to look at, instead of, so we had the co, we write it as a co-limit of some open exhaustion of U alpha, and then co B of co will be replaced by the limit of co b of u alpha. And this is a pro object in cut infinity. Okay, so this is the important object which allows to, let's say, effectively complete the categorification problem I was talking about. So in the remaining 5 minutes, I would just like to make some comments and raise some questions. So the thing that really somehow bothers me the most is that it's quite annoying that so on one side we would like to consider things like this limit of co b u alpha, where u alpha is some quasi-compact open exhaustion. But on the other side, we also want to consider things like pro quasi-co of x. And I don't have time to explain this, unfortunately, so I promised in cut. But this is also a very interesting thing in algebraic geometry, especially to study deformation theory, because inside this thing live the pro-cotangent complex, and we have a decent, let's say, complex. We have a decent theory of this thing that has been developed by Rosenblum and Galesbury. But so, like, how to say? When I say that we want to consider things like this, I mean we would like to have a complete theory. So, for instance, we would like to have a base change theorems, and both theorems in both settings are somehow consequences of the base change for the more natural object gadget, which is co b on some quasi-compact guy, or in this case, suppress the pro. And at the same time, these two things feel like they are related, to me at least. But it's not quite clear in which word I should compare these and these. So this is something that is completely only sensitive to the, I mean, it only exists, it only produces something bigger when the stack is not quasi-compact. And this thing, even in the affine case, produces something bigger. So somehow I would expect these to live naturally inside some nice theory of pro-quasi-coherent sheaves. But it's not so easy to compare. It's not even clear to me how to compare, in the sense that this is an Ind object, and I don't have a natural intuition. So this side, on the other hand, is just an ordinary category, and it doesn't feel like we have enough information there to recover something like this. So somehow the solution that I expect is that we should look at both in the cut and things of the form pro C, where C is a category, as enriched categories, and try to find a uniform theory dealing with both. And well, I mean, enrich, and then I stop. This enriched, there is some.
Mauro,
Yeah.
you're frozen. You're frozen.
Ah, sorry.
I mean, you are not frozen, but the okay.
Yeah. Yeah. So let me just say one last thing, is that enriched categories probably, but I'm not sure. The good framework should be either condensed or pyknotic framework. Definitely, this side. I mean, I have some more than some ideas. Let's say how to improve the theory developed by Nick and Dennis by working in this kind of framework. And the expectation, but I have no idea, is that these categories would naturally fit inside this extended framework. And so, okay, the final conclusion is that I kind of expect, and you are, I mean, if you want to contradict me, you are free to do it. And if you have better ideas, I'm very curious to listen. But I kind of expect that Ind-cat and pro-cat should be taught as enriched in pro-Ind spaces or something better. Like pyknotic or condensed spaces. Something like this. So this is the upshot. It's an expectation. I don't know how to make sense of this. I just wanted to point out some example that I had to confront during my daily life as a researcher in algebraic geometry, and that I don't know to answer. I don't know the answer also. Yeah, so that's it.
Okay, thank you very much, Mauro. We are a little bit late in time, so we have time maybe for one question, even though I would have many to ask. So, so thank you to Mauro. And if someone, so we thank the speaker quickly with a silent round of applause. Now, if someone wants to ask a question, please unmute yourself and ask your question. Okay, if no one wants to, maybe I have one question. So I think these enrichments you have in mind are compatible somehow, because when you look at pro-Ind things, these are going to be inside some pyknotic sheaves over Ind stuff, right?
Yeah, absolutely.
So after all,
yes. I mean, the enrichment on these, and I mean, passing from this to this is not a problem.
It's a kind of inclusion after.
Yeah, absolutely. No, I mean, I totally. So the message I want to pass is that if you ever open the book of Gaisgori Rosenblium, there is a theory of pro-quasi-coherent shifts that is probably outdated now. I mean, can be made outdated with little effort. So if someone wants to do it, it's a good thing to do. That's the first thing. And the second thing is that there is this weirder thing that somehow I expect to include in this bigger framework, but it's not quite clear to me. It would be nice just for me, because I have to prove Bayes change in 3 different ways, I mean, for 3 different kind of objects. And it feels like everything is completely formal. So I would just have one framework, I prove it once, and then it's done. And I never do it again. That's it. So yeah, two messages.
I would have more comments, but I have to stop myself. And so I would say thank you. We thank the speaker one last time. Thank you again, Mauro, for coming today. Very interesting talk.
Thanks for the invitation.
Thank you, definitely. And now I would say